Welcome to our lecture on Group 17 elements, commonly known as the halogens. In this first part of our series, we will explore the fascinating world of fluorine, chlorine, bromine, and iodine. These elements naturally exist as diatomic molecules and share a general outermost electronic structure of ns2-np5, which drives their unique chemical behaviors. Halogens are indispensable to modern civilization. From the chlorine that purifies our drinking water to the iodine that is essential for human thyroid health, these elements are everywhere. However, the exact same chemical power that makes them so useful in manufacturing and medicine can also create severe environmental and health challenges if they are not managed responsibly. Let's start by looking at the basic physical properties of the halogens at room temperature. Notice the distinct progression. Fluorine is a pale yellow gas, chlorine is a pale green gas, bromine is a dense red-brown liquid, and iodine is a black solid that gives off a beautiful violet vapor. This variation in physical state is a classic periodic trend.
Why exactly do we see this shift from gas to liquid to solid as we move down the group? As the atomic mass of the elements increases, the overall molecular mass increases as well. This leads to stronger intermolecular van der Waals forces of attraction. These stronger forces pull the molecules closer together, fundamentally changing their physical state.
Directly related to their physical states are the melting and boiling points of the halogens, which steadily increase as you move down the group. Because the van der Waals forces become stronger with increasing molecular mass, you need to supply significantly more heat energy to overcome these forces and change the substance's state. Now, let's discuss the energy required to break these molecules apart. Bond dissociation energy is the heat needed to break 1 mole of covalent bonds, while atomization energy is the heat needed to form 1 mole of gaseous atoms. Generally, this energy decreases down the group because the atoms get larger and the bonds get longer and weaker. But notice the order. Chlorine is highest and fluorine is surprisingly at the bottom. You might be wondering why fluorine breaks the trend with an abnormally low bond dissociation energy. It comes down to its tiny size. Because the fluorine atoms are so small, the bond length is very short. This forces the non-bonding electron pairs on adjacent atoms incredibly close together. The resulting electrostatic repulsion between these lone pairs actually weakens the covalent bond. Looking at the atomic structure, the atomic and ionic radii naturally increase as we go down the group because each subsequent element has an additional electron shell. Consequently, the first ionization energy decreases down the group. As the outermost electrons get further from the positive pole of the nucleus and experience more shielding from inner electrons, they become easier to remove. Electronegativity, which is the ability of an atom to attract a bonding pair of electrons, strictly decreases down the group, with fluorine being the most electronegative element on the periodic table. Similarly, electron affinity, the energy released when an electron is added to a neutral atom, generally becomes less negative down the group, though chlorine actually has a slightly higher affinity than fluorine due to fluorine's small, crowded electron cloud. Because halogens react primarily by gaining electrons, their overall chemical reactivity decreases as they get larger and less able to attract incoming electrons. This is reflected in their standard electrode potentials. Fluorine has a very high positive electrode potential, making it incredibly reactive, while iodine's lower potential indicates it is a much weaker oxidizing agent. Let's delve deeper into their role as oxidizing agents. Because their oxidizing power decreases down the group, a lighter, more reactive halogen can displace a heavier halide ion from a solution. For instance, if you bubble chlorine gas through a solution of bromide ions, the chlorine will steal their electrons, displacing them to form red-brown bromine. We can explain this trend in oxidizing power using thermodynamics. The process of a halogen becoming an aqueous ion involves atomization, gaining an electron, and finally hydration. The major determining factor here is the enthalpy of hydration. Smaller ions, like fluoride, have much higher hydration energies. This makes the overall reaction highly exothermic and highly favorable, making fluorine the strongest oxidizing agent. Because iodine is the weakest oxidizing agent of the 4 common halogens, it is incredibly useful in a laboratory technique called iodometry. We can estimate the concentration of an unknown oxidizing agent by reacting it with excess iodine ions to liberate iodine. We then titrate that liberated iodine against sodium thiosulfate. The moment the dark blue-black starch complex disappears, we've reached our endpoint and can calculate the exact amounts involved. Now let's look at specific chemical reactions, starting with metals. Halogens react vigorously with heated metals to form ionic salts called metal halides. In these redox reactions, the metal is oxidized and the halogen is reduced. As expected, the vigor of this reaction decreases down the group, with fluorine reacting explosively, while iodine requires much more coaxing. Halogens also react directly with nonmetals to form covalent compounds. When reacting with hydrogen to form hydrogen halides, the trend in reactivity is very obvious. Fluorine will explode with hydrogen, even in the dark. Chlorine needs sunlight, bromine needs heat, and iodine barely reacts at all, forming an equilibrium mixture. They also react readily with elements like sulfur and phosphorus. When halogens dissolve in water, they undergo a special type of redox process called a disproportionation reaction. This means the halogen is simultaneously oxidized and reduced. For example, chlorine reacts with water to form hydrochloric acid and chloric 1 acid. Bromine does something similar, while iodine's reaction with pure water is practically negligible. Here is a classic laboratory scenario. If you try to dissolve iodine crystals in pure water, almost nothing happens because iodine is nonpolar and water is polar. However, if you add potassium iodide to the water first, the iodine dissolves beautifully. This happens because the iodine molecules react with the iodide ions to form a highly soluble triiodide complex ion. Halogens react much more completely with alkalis than with water. If you bubble chlorine through cold, dilute sodium hydroxide, it undergoes disproportionation to form sodium chloride and sodium chlorate 1, commonly known as sodium hypochlorite. This resulting solution is actually the active ingredient in household bleach. If we change the conditions and use hot, concentrated alkali instead, the reaction is driven a step further. The halate 1 ions that initially form are unstable at high temperatures and further disproportionate. The final products are a halide salt and a halate V salt. For example, chlorine yields sodium chloride and sodium chlorate V. You might wonder why halogens dissolve so much better in sodium hydroxide than in pure water. It's a great example of Le Chatelier's principle. When the halogen slightly dissolves in water, it forms acids. The hydroxide ions from the alkali immediately neutralize those acids. By constantly removing the products of the equilibrium, the system is forced to shift to the right, pulling more and more halogen gas into solution. These reactions produced highly useful compounds. Sodium chloride 1 is a powerful bleach and antiseptic, while sodium chloride 5 is produced on an industrial scale via the electrolysis of hot brine. It is important to note that fluorine is an exception here. Because it is the most electronegative element and lacks d orbitals, it cannot expand its octet to form these types of oxygen-rich compounds. Moving on to the hydrogen halides, we can prepare hydrogen fluoride and hydrogen chloride in the laboratory by reacting their solid salts with concentrated sulfuric acid. A crucial safety note for hydrogen fluoride: it aggressively attacks the silica in glass, so it must always be stored in specialized plastic or lead containers. Preparing hydrogen bromide and hydrogen iodide requires a different approach. We cannot use concentrated sulfuric acid because it is a strong enough oxidizing agent to turn the HBr and HI back into elemental bromine and iodine. Instead, we drip water onto a mixture of the halogen and red phosphorus, or we pass hydrogen sulfide gas through an aqueous solution of the halogen. Let's examine the physical properties of these hydrogen halides, starting with their ionic character. Because halogens are highly electronegative, the covalent bond with hydrogen is polar, creating partial charges. As we move down the group, the halogens become less electronegative, meaning the charge separation decreases, and the bond becomes less ionic and more purely covalent. When dissolved in water, these hydrogen halides act as acids. Interestingly, their acidic strength increases down the group. Hydrogen iodide is a much stronger acid than hydrogen fluoride. This is because as the halogen atom gets larger, the hydrogen-halogen bond gets longer and weaker. A weaker bond means the proton is much more easily released into the solution. What about oxoacids, like the chloric acids? Here the rule is a bit different. The acidic strength increases with the number of oxygen atoms. Oxygen is highly electronegative. The more oxygen atoms present, the more they pull electron density away from the oxygen-hydrogen bond through a negative inductive effect. This weakens the OH bond, making it easier to donate a proton. In the laboratory, we use qualitative analysis to identify which halide ions are present in a sample. A primary test involves adding concentrated sulfuric acid to the salt solid. Bromides will immediately give off a red-brown bromine vapor, and iodides will produce a striking dark purple iodine vapor. Chlorides require a bit of heat and an oxidizing agent, like manganese dioxide, to release a pale green chlorine gas.
Another common test uses aqueous lead-2 nitrate. When added to halide solutions, it forms distinct precipitates. Chloride forms a white precipitate that uniquely dissolves when heated and reappears when cooled. Bromide also forms a white precipitate, but it barely dissolves in hot water. Iodide stands out by forming a bright yellow precipitate of lead-2 iodide. The silver nitrate test is highly effective for distinguishing halides based on both the color and solubility of the resulting precipitates. Chloride forms a white precipitate that easily dissolves if you add excess ammonia. Bromide and iodide both form pale yellow or cream precipitates, but unlike chloride, they will not dissolve in excess ammonia. Let's summarize the specific confirmatory tests for chloride ions. You are looking for a white precipitate with lead nitrate that dissolves on heating, a white precipitate with silver nitrate that dissolves in ammonia, or the evolution of acidic white fumes or bleaching green gas when treated with sulfuric acid. For bromide ions, the confirmatory tests yield distinct colors. You'll see a cream precipitate with silver nitrate that ignores ammonia. If you use chlorine water to displace the bromine and extract it with an organic solvent like carbon tetrachloride, you'll get a beautiful orange organic layer. And of course, sulfuric acid yields red-brown vapors. Finally, iodide ions provide some of the most visually striking test results. Lead nitrate gives a bright yellow precipitate. Silver nitrate gives a pale yellow precipitate that slowly turns gray in the light. Extracting displaced iodine into an organic layer yields a rich purple solution, matching the violet vapors produced during the sulfuric acid test. Let's review a critical concept we touched on earlier. Why can we use sulfuric acid to make hydrogen chloride, but not hydrogen bromide? It's because hydrogen chloride is a weak reducing agent and survives the acidic environment. Hydrogen bromide, however, is a strong reducing agent. The sulfuric acid will immediately oxidize it into elemental bromine gas. To get around this, we have to use a weaker acid, like phosphoric acid. To wrap up this segment, let's look at the real-world applications and risks of Group 17 elements. They are essential for public health, like chlorine in water treatment and iodine in our diet, as well as in industrial materials like PVC. However, their high reactivity means they can be toxic, corrosive, and environmentally persistent if mismanaged. Understanding these dual roles of halogens provides a crucial foundation as we move forward to examine more complex chemical systems in our next session. Picking up with the synthesis of halogens, let us look at how chlorine is prepared in the laboratory. The most common method involves removing hydrogen from concentrated hydrochloric acid using a strong oxidizing agent. When the mixture is heated, the oxygen from the oxidizing agent combines with the hydrogen from the acid to form water, liberating chlorine gas. The metal from the oxidizing agent then combines with the remaining chloride to form a metal chloride. Several different oxidizing agents can be used for this reaction. Manganese dioxide is a classic choice, reacting with 4 moles of hydrochloric acid to produce manganese 2 chloride, water, and chlorine gas. Lead-4 oxide and trilead tetroxide follow a very similar pattern, producing lead-2 chloride. In all these specific cases, heat must be applied to the flask to drive the reaction forward. When we use an exceptionally strong oxidizing agent like potassium permanganate, the reaction is so vigorous that external heat is not required at all. The permanganate reacts with 16 moles of hydrochloric acid to yield a large volume of chlorine gas. Potassium dichromate can also be used as the oxidizing agent, though unlike permanganate, it does require heating to proceed efficiently. Let us examine the physical setup for this preparation. The chlorine gas generated in the reaction flask is not pure. It contains unreacted hydrogen chloride vapors and moisture. To purify it, the gas is first bubbled through a wash bottle containing water, which dissolves and removes the highly soluble hydrogen chloride gas. Next, it passes through concentrated sulfuric acid, which acts as a drying agent to remove water vapor. Finally, because chlorine is denser than air, it is collected in a cylinder by the upward displacement of air. An alternative and much cheaper method uses sodium chloride instead of pure hydrochloric acid. A mixture of sodium chloride and manganese dioxide is heated with concentrated sulfuric acid. This happens in stages. First, the sulfuric acid reacts with sodium chloride to generate hydrochloric acid in situ. Then, the manganese dioxide oxidizes this newly formed hydrochloric acid to liberate chlorine gas. Additionally, the manganese chloride produced can further react with sulfuric acid to release even more hydrochloric acid for oxidation. When we combine those intermediate steps, we get this elegant overall equation. 2 moles of sodium chloride react with 1 mole of manganese dioxide and 3 moles of sulfuric acid.
The products are sodium hydrogen sulfate, manganese 2-sulfate, water, and our desired product, chlorine gas. This method is highly efficient for laboratory settings because sodium chloride is inexpensive and readily available. A third laboratory method involves bleaching powder, chemically known as calcium hypochlorite chloride. By simply placing bleaching powder in a flask and adding a dilute mineral acid, such as hydrochloric or sulfuric acid, chlorine gas is rapidly evolved. As you can see from the equations, the acid reacts with the bleaching powder to form a calcium salt, water, and chlorine. No external heat is required for this setup. Moving to an industrial scale, chlorine is manufactured by the electrolysis of brine, which is a concentrated sodium chloride solution. In a cell with a graphite anode and a mercury cathode, chloride ions migrate to the anode and are oxidized to form chlorine gas. At the cathode, sodium ions are reduced and dissolve into the mercury to form a sodium amalgam. This amalgam is then tapped off and reacted with water to produce sodium hydroxide and hydrogen gas, while the mercury is recycled. Chlorine is also obtained industrially as a major byproduct of the Downs process, which is primarily used to extract sodium metal. Here, molten sodium chloride is electrolyzed. Calcium chloride is added to the mixture to significantly lower the melting point from 1074 Kelvin down to 800 Kelvin, saving a massive amount of energy. During electrolysis, pure chlorine gas bubbles off at the anode, making this a highly valuable dual-purpose industrial process. Before we move on to other halogens, it is important to note the practical applications of chlorine. Its most critical use in everyday life, particularly in regions like Uganda, is in water treatment and purification. Chlorine is a powerful disinfectant. When added to drinking water supplies, it effectively eradicates harmful microorganisms, including dangerous bacteria, viruses, and parasites, ensuring public health and safety. Now let us look at the laboratory preparation of bromine. The underlying chemistry is nearly identical to the sodium chloride method we saw earlier, but we use sodium bromide instead. A mixture of sodium bromide, manganese dioxide, and concentrated sulfuric acid is heated. Because bromine is a volatile liquid, the evolved vapors are passed through a condenser surrounded by cold water, allowing liquid bromine to be collected in a receiving flask. For iodine, the preparation method adapts to its unique physical properties. We heat a mixture of potassium iodide, manganese dioxide, and concentrated sulfuric acid in a beaker. Instead of a standard condenser, a round bottom flask filled with cold water is placed directly over the beaker. As the iodine is produced, it turns into a purple vapor and then immediately sublimates, depositing as solid, dark gray iodine crystals on the cold underside of the flask. Turning our attention to fluorine, we encounter the most chemically reactive nonmetal on the periodic table. Fluorine is a pale yellow gas with an irritating smell. Because it boasts the highest electronegativity of all elements, at 4.0, it will readily displace any other halogen from its ionic halides. Interestingly, the fluorine molecule has an abnormally low bond energy, meaning it easily breaks apart to form incredibly strong, highly exothermic covalent and ionic bonds with almost every other element. Like other elements in the second short period, fluorine exhibits anomalous behavior compared to the rest of its group. This unique chemistry stems from several key factors. It has the smallest atomic radius and the highest electronegativity. It also has the highest positive standard electrode potential and the lowest bond energy. Furthermore, fluorine completely lacks d orbitals in its valence shell, restricting its bonding capabilities, and its tiny fluoride ion has the lowest polarizability among the halogens. These underlying factors lead to specific anomalous properties. First, fluorine only ever exhibits an oxidation state of -1. It is too electronegative to donate electrons and lacks d orbitals to expand its octet. However, it forces other elements into their highest oxidation states, forming compounds like sulfur hexafluoride, high charge density cations like aluminum, whereas aluminum chloride is covalent. The anomalies continue with its hydride, hydrogen fluoride. Because fluorine is so electronegative, the hydrogen fluoride bond is extremely polar, leading to strong intermolecular hydrogen bonding. This gives hydrogen fluoride an unexpectedly high boiling point. This hydrogen bonding also allows hydrogen fluoride to react with alkalis to form unique acid salts, such as potassium hydrogen difluoride, a reaction not seen with the hydrides of other halogens. When it comes to water, fluorine reacts completely differently than chlorine or bromine. Due to its massive oxidizing power and highly positive standard electrode potential, fluorine reacts vigorously with water to liberate oxygen gas.
As the equations show, fluorine is reduced to fluoride ions while simultaneously oxidizing the oxygen in water, resulting in the formation of hydrofluoric acid and pure oxygen gas. Finally, fluorine's reaction with strong alkalis depends entirely on the temperature and concentration. With cold dilute alkalis like sodium hydroxide, fluorine reacts to produce oxygen difluoride gas. However, if the alkali is warm and concentrated, the reaction is driven further to liberate pure oxygen gas instead. We will continue exploring how these unique properties influence the broader chemistry of the halogens in the next segment. Moving right into the practical applications of halogens, let's look at how chlorine is heavily utilized in water treatment. Large-scale municipal systems, like the National Water and Sewerage Corporation, add chlorine at treatment plants to ensure the tap water circulating to homes is safe and free of pathogens. In areas without piped infrastructure, such as rural communities or refugee camps, portable chlorine tablets are a lifesaver for purifying water drawn from rivers or wells. Additionally, recreational facilities rely on chlorine to maintain sanitary conditions in swimming pools. To supply these massive applications, chlorine must be produced on an industrial scale. This diagram illustrates the downcell, a common method for producing chlorine gas alongside sodium metal. By passing an electric current through molten sodium chloride, the compound is separated. Chlorine gas bubbles up at the central carbon anode and is collected through the top outlet, while liquid sodium metal forms at the iron cathode. The iron screen prevents the highly reactive sodium and chlorine from recombining. On a smaller scale, chlorine is a staple in household cleaning. Many common bleaching agents sold in stores contain sodium hypochlorite, which is an active chlorine compound. When you use bleach to clean bathrooms, wipe down kitchen surfaces, or wash white clothes, you are utilizing chlorine's powerful oxidative properties to destroy bacteria and viruses. This routine hygiene is critical for preventing the spread of severe household and community diseases, such as cholera and typhoid. In public health, chlorine's rapid germ-killing ability makes it a frontline defense during severe disease outbreaks. Health workers rely on carefully mixed chlorine solutions to establish emergency sanitation zones when battling highly contagious diseases like cholera, Ebola, and COVID-19. It is used comprehensively to disinfect hands, sterilize medical equipment, and mop hospital wards. During severe epidemics, you will even see public health teams spraying chlorine solutions across public places and markets to break the chain of transmission. Beyond sanitation, factories rely heavily on chlorine for manufacturing. In the textile and paper industries, chlorine is the primary agent used to bleach raw materials, turning natural fibers and wood pulp bright white. It is also a fundamental building block in the chemical industry. For example, the PVC pipes widely used in construction and plumbing stand for polyvinyl chloride, meaning they are made using chlorine compounds. Additionally, chlorine is used to synthesize important organic solvents like chloroform. Farmers also utilize chlorine compounds to maintain animal health and farm hygiene. By regularly disinfecting poultry houses and livestock shelters with chlorine-based sprays, farmers can drastically reduce the spread of infections among their herds and flocks. It is also vital in the dairy industry, where chlorine is used to clean milking equipment, ensuring that bacteria do not contaminate the milk supply. Furthermore, treating the animals' drinking water with mild chlorine doses keeps the livestock healthy. In the food industry, chlorinated water is essential for safety and preservation. Before fruits and vegetables make it to the grocery store, they are often washed in a mild chlorine solution at the processing plant to remove soil-borne pathogens and pesticide residues. The heavy machinery and conveyor belts used to process these foods are also sanitized with chlorine to prevent cross-contamination, ensuring that the food arriving at restaurants and homes is safe to consume. Hospitals and laboratories require strictly sterile environments, and chlorine-based disinfectants are highly effective here. They're used to sterilize surgical instruments and wipe down laboratory surfaces where infectious samples might be handled. Chlorine is also applied to medical waste areas to neutralize biohazards before disposal. This rigorous application is a primary strategy in preventing hospital-acquired infections, protecting both vulnerable patients and healthcare workers. During emergencies, such as floods or in refugee settlements, normal infrastructure often collapses and access to clean water is compromised. Relief organizations deploy chlorine as an immediate, scalable solution. By treating standing water and providing chlorine drops for drinking water, they can maintain basic sanitation even in the harshest conditions. This rapid response is absolutely critical for preventing secondary disasters, namely massive outbreaks of waterborne diseases. Despite its immense utility, chlorine does have notable disadvantages that must be managed. First are the aesthetic issues.
If water treatment plants use excess chlorine, it leaves drinking water with an unpleasant chemical smell and taste. Furthermore, chlorine is not a silver bullet. Certain resilient microorganisms and parasites have developed thick outer shells that allow them to resist standard chlorine treatments, meaning water systems sometimes need additional filtration methods. Seriously, more concerning are the chemical and environmental risks. When chlorine reacts with natural organic matter in water, it can form toxic disinfection byproducts, or DBPs, such as trihalomethanes, which are potentially carcinogenic over long-term exposure. Direct overexposure to high concentrations of chlorine gas or liquid can severely irritate human skin, eyes, and the respiratory system. Finally, if heavily chlorinated wastewater is discharged into rivers or lakes, it can be highly toxic to aquatic ecosystems, requiring careful dosage control. Shifting our focus to another halogen, fluorine plays a highly specific role in human health, primarily in dentistry. Fluoride, derived from fluorine compounds, is a standard ingredient in toothpaste and is often added to public drinking water supplies. It works by chemically integrating into the tooth enamel, making it significantly harder and more resistant to the acid attacks that cause tooth decay or dental caries. This controlled application has been a massive public health success globally. However, the balance of fluoride is delicate. While low concentrations are beneficial, excess fluoride exposure leads to dental fluorosis, which causes permanent white or brown staining on the teeth. In severe cases of high long-term exposure, it can cause skeletal fluorosis, a painful condition that damages bones and joints. This is particularly a concern in regions where the natural groundwater is already heavily contaminated with high levels of fluoride, requiring careful monitoring to prevent overexposure. Next, we examine chlorofluorocarbons, or CFCs. Historically, these compounds were considered miracle chemicals for industrial and consumer use. Because they are incredibly stable, non-toxic, and non-flammable, they were the perfect safe choice for refrigerants in fridges and air conditioners, as well as propellants in aerosol spray cans. They were highly efficient at cooling and posed no immediate danger to the people using them. The fatal flaw of CFCs was discovered later: their impact on the upper atmosphere. Because they are so stable, CFCs drift all the way up into the stratosphere. There, intense solar radiation breaks them apart, releasing highly reactive chlorine radicals. These radicals catalyze the destruction of ozone molecules, leading to severe ozone layer depletion, famously creating the ozone hole over Antarctica. This allowed dangerous UV radiation to reach Earth, increasing skin cancer rates, which ultimately led to the Montreal Protocol, a global agreement that successfully phased out CFCs. Moving down the halogen group, bromine is heavily utilized in fire safety. Bromine compounds are manufactured into flame retardants that are embedded into everyday items like upholstered furniture, plastic electronics casings, and textiles. The distinct advantage here is life safety. When exposed to heat, these bromine compounds interfere with the chemical reaction of the fire, significantly slowing its spread and giving people crucial extra minutes to escape a burning building. While they save lives in fires, brominated flame retardants create long-term pollution challenges. Many of these compounds are classified as persistent organic pollutants, meaning they do not easily break down in nature. They bioaccumulate in the food chain and have been linked to potential endocrine disruption in humans. Furthermore, when electronic waste containing these retardants is improperly burned, it releases highly toxic brominated compounds into the air and soil. Finally, let's look at iodine, which is absolutely critical for human nutrition. To combat widespread deficiencies, many countries add iodine to standard table salt. This simple, incredibly cheap intervention prevents severe thyroid disorders, such as goiter, which is an enlargement of the thyroid gland. More importantly, adequate iodine is essential for normal brain development in children. We will explore the environmental and health concerns associated with iodine in our next segment. Let's look at how hydrogen bromide reacts with concentrated sulfuric acid. Sulfuric acid acts as a weak oxidizing agent here. It oxidizes the hydrogen bromide into liquid bromine, which we often observe as a red-brown vapor. In the process, the sulfuric acid itself is reduced to sulfur dioxide gas. If we look at the oxidation states, sulfur goes from +6 in sulfuric acid down to +4 in sulfur dioxide, gaining electrons. Meanwhile, the bromide ions are oxidized from -1 to 0 in elemental bromine. Moving to hydrogen iodide, we see a much more dramatic reduction. Because hydrogen iodide is a stronger reducing agent than hydrogen bromide, it reduces the sulfur in sulfuric acid all the way from an oxidation state of +6 down to -2, forming hydrogen sulfide gas.
The hydrogen iodide is oxidized to solid iodine, which appears as a violet vapor or black solid. This deeper reduction highlights the trend we discussed earlier. Reducing power increases as we go down the halogen group. When we heat solid halide salts with concentrated sulfuric acid, the outcomes depend on the specific halide. For chloride salts, like sodium chloride, the reaction stops at displacement. We get sodium hydrogen sulfate and hydrogen chloride gas, which appears as misty white fumes. Hydrogen chloride is too weak of a reducing agent to react further. However, for bromide and iodide salts, the initially displaced hydrogen bromide and hydrogen iodide are strong enough reducing agents to undergo secondary oxidation reactions, producing elemental bromine and iodine. Let's break down the reaction with sodium bromide step by step. First, the sulfuric acid displaces the hydrogen bromide gas, but because the mixture is hot and concentrated, a second reaction immediately follows. The newly formed hydrogen bromide reacts with more sulfuric acid, getting oxidized to bromine while reducing the acid to sulfur dioxide. By combining these two steps, we get the overall equation showing sodium bromide and sulfuric acid, producing sodium hydrogen sulfate, sulfur dioxide, water, and bromine. The process is similar for sodium iodide, but the secondary oxidation is more extensive. The initial displacement yields hydrogen iodide. Then, 8 molecules of hydrogen iodide react with sulfuric acid to produce hydrogen sulfide gas and iodine. The overall equation reflects this heavy consumption of reactants. Interestingly, side reactions can also occur here. For example, any sulfur dioxide produced can react with the hydrogen sulfide to precipitate solid yellow sulfur. Now let's look at a much stronger oxidizing agent, acidified potassium manganate 7. This reagent is powerful enough to oxidize hydrogen chloride, hydrogen bromide, and hydrogen iodide into their respective halogens. Hydrogen fluoride remains unaffected. When hydrochloric acid reacts, it decolorizes the vibrant purple manganate solution, producing pale green chlorine gas. This specific reaction is exactly why we never use hydrochloric acid to acidify potassium manganate 7 in titrations, as it would consume the reagent and release toxic chlorine gas. Nitric acid sits between sulfuric acid and potassium manganate 7 in terms of oxidizing strength. It successfully attacks hydrogen chloride, bromide, and iodide, oxidizing them to chlorine, bromine, and iodine respectively. When concentrated nitric acid reacts with hydrogen iodide, the nitric acid is reduced to nitrogen dioxide, a brown gas. Interestingly, if we boil the mixture, the oxidation can go even further, converting the iodide ions all the way into iodide 5 ions, forming iodic acid. Shifting gears, let's explore the oxyacids or oxoacids of the halogens. As the name suggests, these are acids that contain oxygen. They are fascinating because they exhibit both acidic and oxidizing properties. Iodine and bromine form several of these, but the most comprehensive series belongs to chlorine. Chlorine forms 4 distinct oxyacids: chloric 1 acid, also known as hypochlorous acid, chloric 3 acid, chloric 5 acid, and chloric 7 acid, commonly called perchloric acid. The properties of these chlorine oxyacids follow very clear, predictable trends based on their oxygen content. As the number of oxygen atoms increases, both the thermal stability and the acid strength increase. Therefore, chloric 7 acid, or perchloric acid, is the most stable and the strongest acid of the group. Conversely, the oxidizing power follows the exact opposite trend. The acid with the fewest oxygen atoms, hypochloric acid, is actually the strongest oxidizing agent among them. Why does acid strength increase with more oxygen atoms? We can explain this by looking at the stability of the anions formed when these acids ionize in water. When an acid loses a proton, it leaves behind a negatively charged ion. In the perchlorate ion, ClO4-, that negative charge is delocalized or spread out over 4 highly electronegative oxygen atoms. This resonance stabilizes the ion immensely. A more stable anion means the acid dissociates more readily, releasing more protons and acting as a stronger acid. We can also view this from the perspective of the molecular structure before it ionizes. Look at the structures of these acids. In perchloric acid, the central chlorine atom is double bonded to 3 oxygen atoms. These highly electronegative oxygen atoms pull electron density towards themselves, away from the chlorine, which in turn pulls electron density away from the oxygen-hydrogen bond. This inductive effect weakens the OH bond significantly, making it much easier for the hydrogen ion to break free, compared to hypochloric acid, which has no double-bonded oxygens. Finally, let's briefly touch on a practical application of halogen chemistry: fluorine compounds in dental health.
Fluorides are widely used in toothpaste and water treatment because they significantly reduce tooth decay and improve overall dental health across all age groups. It is a highly cost-effective form of preventative healthcare. However, as with any chemical intervention, it's important to monitor environmental and health concerns to ensure that fluoride exposure remains at safe, beneficial levels.
To wrap up our discussion on halogen chemistry, let's review the key takeaways. We've seen that the reducing power of hydrogen halides increases as we move down the group, with hydrogen iodide being the strongest reducing agent. We also explored how various oxidizing agents interact with these halides, displacing the free halogens. Finally, we examined the fascinating trends in the oxyacids of chlorine, noting that as the oxygen content increases, the acid becomes stronger and more stable, but its oxidizing power actually decreases. Thank you for following along with this comprehensive look at the halogens.